Hey Wheat North, Mr. Yergler here. We've talked about different types of reactions, 5 different types. Now we're going to dive a little bit deeper into double replacement reactions. So the goal here is to identify the double replacement reaction, predict the products, and balance the reaction. And part of predicting the products is figuring out what is going to be insoluble. So you're going to need your orange periodic table for that. So go ahead and grab that, and let's get started. We've talked about single replacement, where we just have a single element. Usually this is a metal by itself with a compound that involves a metal and a nonmetal, so an ionic compound, where one thing is switching places, right? Just the metals are switching places. A is going to go in and kind of kick out B, so to speak, as kind of shown in this picture, right? This is a little bit different from double replacement. In double replacement, we always have two ionic compounds. So there's always AB and CD. Some sort of format like this. And notice that the guys are switching partners, right? The guys represent metals. The metal is always written first, and the metal is always a cation. It's always positive. So the two positives are not going to go together. They're going to switch places so that we still have a positive with a negative, right? In a double replacement reaction, you might want to put a star next to this. This will always, always, always have two ionic compounds. If you have just one thing by itself, there's no way for it to be double replacement. So notice that they're switching partners, and that this guy, C, ends up with this girl, B, right? So CB and then AD. So positive, negative, positive, negative. They just switched partners. All right, let's look at an example of this. Sodium chloride, NaCl. Now normally what you're used to seeing is table salt. That's solid sodium chloride. And notice the little parentheses S, that indicates a solid. That's where we have like a group of molecules kind of clumped together, and ionic compounds are always in this crystal structure where it's just negative, positive, over and over and over again. Now when we dissolve this in water, what happens is it's called dissociation or ionization. We go from the solid to the aqueous form of salt. The water molecules, which aren't shown in the picture, have literally pulled the ions apart, and so they're just kind of freely floating around in the solution. Another example would be silver nitrate. So silver is represented by the red circle, and nitrate I'm representing with just a single blue circle because it's a polyatomic ion. It kind of acts as one unit. Now we can have silver nitrate as a solid, but we can also have it dissolved in water, in which case the water molecules have pulled the ions apart and the ions themselves are kind of floating around separately. So we've gone from silver nitrate solid to silver nitrate aqueous, right? Put a little AQ in there to indicate that it's dissolved in water. All right, now if we mix these two, then we'll just have all the ions floating around in the same container. And this is where the solubility chart comes in super handy. So let's switch real quick to the solubility chart and take a look at that. So grab your periodic table and let's take a look at this solubility chart. So I have a digital version here, but you should be looking at yours on your periodic table. Now the two reactants that we talked about were sodium chloride, right? So notice that all the metals are on this side. This is on the back of your periodic table. And all the nonmetals are up here, right? Let's find sodium chloride. So sodium is right here. Chloride is the fourth one right here. So where they meet, notice that it says AQ. That means aqueous, right? So that means it's dissolved in water, or it can be dissolved in water. And we know from experience that sodium chloride dissolves in water, right? Table salt. The other reactant was silver nitrate. So we want to look at silver, and then notice that nitrates, every single nitrate is aqueous, and so silver nitrate is going to be aqueous. And that means that it can also be dissolved in water, right? Now, when we do the double replacement reaction, let me switch back to the pictures. They've switched places, right? Notice how I'm drawing this. The silver is now with the chlorine, so my red cation here, my silver ion, is now with my negative anion from the other reactant, right? So we have silver chloride and we have sodium nitrate, right? So silver chloride, if we look for silver and chloride is right here, notice that it says PPT. This means precipitate, which means that silver chloride does not dissolve in water. You can't dissolve silver chloride in water. It just doesn't dissolve. Water molecules essentially are not strong enough to pull the two ions apart. And so this forms a solid instead of aqueous. It comes out of solution. If we switch back to the pictures here, this is why I drew these ions as together and the other ones as separate, right? Because silver chloride is a solid, notice my little S, and sodium nitrate is still aqueous. So the silver chloride will actually settle out of the solution, and you'll see this solid kind of sediment forming at the bottom. Kind of like if you have sand or something else that doesn't dissolve in water. It always settles to the bottom. All right, let's look at a few more examples real quick. Copper 2 carbonate and zinc nitrate, if these are our reactants, predict our products. Writing it out in words like this, it makes it super easy to predict the products. We're just going to switch the metals. So if you want to even write these out and then draw a line connecting zinc and carbonate, and then draw a line connecting copper and nitrate, right? So we'll end up with zinc carbonate and copper 2 nitrate. Now we also want to write the formulas for this so that we can have a balanced equation. So copper 2 nitrate, the 2 means that copper is +2, and carbonate is a polyatomic ion. It has a -2 charge, and so we only need one of each. Zinc nitrate, zinc is +2 always, and nitrate is -1. That's why we have 2 nitrates here. Copper 2 nitrate, same thing, +2, and so we need 2 nitrates because they're each -1, and then zinc carbonate is ZnCO3. Now this is already balanced. Now this is where the solubility chart really comes in handy, because we need to identify what is our product that's produced. One of them usually is going to be a solid and the other is going to be aqueous. We need to figure out which one. So again, let's jump over to our solubility chart. One of our products was zinc carbonate. So let's find zinc, it's right here, and carbonate is the third one over, right? So zinc carbonate, it has a little PPT, so it's precipitate. That means it does not dissolve in water. So if we have zinc ions and they happen to run in the same container and they happen to run into carbonate ions, they're going to form a solid zinc carbonate compound that doesn't dissolve. It comes out of solution as a precipitate, as a solid. The other product was copper 2 nitrate. Remember that nitrates are always aqueous. So if we want to find it, it'd be right here. Copper 2 nitrate is aqueous. So that's just going to stay in solution. So we put a little S after the zinc carbonate because that's our solid, that's our precipitate, and copper 2 nitrate stays as aqueous. All right, next example, sodium bromide and barium chloride. Switch partners, so it becomes barium bromide and sodium chloride, and then write the formulas. Go ahead and pause the video and write out those formulas, kind of quiz yourself to make sure you're still good at writing formulas. All right, here they are. Sodium bromide is NaBr, +1 -1, +2, so we need 2 chlorines. Same thing, +2 for barium, so we need 2 bromines, and sodium chloride is NaCl. Now we need to balance this as well. 2 chlorines and 2 bromines means we need a 2 here and a 2 here. Now we need to see what's our solid and what's our aqueous, right? Take a look at your solubility chart, find barium bromide and sodium chloride. Sodium chloride, you should know from experience, is aqueous. Table salt dissolves in water pretty easily, so that's going to be an aqueous solution. The reactants are always aqueous, and so unless it's going to come out of solution as a precipitate, it's just going to stay as aqueous. Barium bromide is actually also aqueous. So picture a cup of salt water, right? It looks just like water. Let's say you add another compound to it, and it doesn't form a solid. It just continues to look like salt water. And so we say that there's no reaction if both products are aqueous. Remember, the reactants are always going to be aqueous. If both products are aqueous, then it's no reaction because it just looks like salt water, which looks like water. We're not creating anything new, right? No, there's no change. There's no physical change that we can observe. And so this would be no reaction. All right, one more example. Go ahead and predict the products, write the formulas, make sure you have a balanced equation, and then look on your solubility chart for the products to see what product is a solid, if any. Okay, bring that to class, bring any questions you have to class, and we'll get a lot of practice there. All right, this is Mr. Yergler signing out.